leaving things alone.
I guess I should share. I will have a lot of academics myself.
So we're very happy to have Michael Toomey from MIT telling us about learning theory-informed trials for Bayesian inference, a case study with early dark energy.
Okay, thank you very much. Yeah, so that is a bit of a mouthful. Yeah, today's talk I'm going to tell you about a paper that will be appearing on the archive. I probably should have just say to appear next week. Using this very interesting new method, well, it's not entirely new, but it's certainly newer for cosmology, physics in general. This machine learning type architecture I'll be talking today. But to sort of build up to the main result of this paper, I'm going to have to do a lot of background. And given the nature of this audience, I have to do a little more than usual. So just a little outline. And also, because of that, feel absolutely free at any time to ask questions. Because I won't be able to go as deep as I would if this was an audience of, say, dedicated cosmologists, for example. But just a quick overview of what I'll be talking about today. I'm going to begin with a review of basic cosmology, just to get everyone on the same page, sort of understand the particular application I want to use to demonstrate this sort of new technique of theory-informed priors. Then I want to do an overview of standard Bayesian inference. So this will be very important for understanding the whole point of why I want to do this very interesting machine learning technique. Then I'm going to introduce the particular model that I want to be testing. This is a very good example that's been extensively studied by myself and others for about 5 or 6 years now. This model of early dark energy that's posed for cosmic tensions, and is a very good test bed or test case for implementing this theory-informed prior machine learning architecture. And then I'm going to do yet another introduction, very brief again, but on machine learning and then this specific architecture I want to use in this particular talk called normalizing flows. And then at the end, we'll actually get into the application. And hopefully, maybe it doesn't all make sense right now, but hopefully as I walk you through, you'll have a better understanding of why this is actually a very interesting tool, very interesting technique to better bridge the gap between theorists and experimentalists. And that'll be part of discussing. So to begin with, because I know this is an audience of people who aren't necessarily in cosmology, I want to begin off by talking about, okay, first of all, what is cosmology, right? And so the bedrock of modern cosmology is the lambda CDM model of cosmology. This is the standard concordance model. There are several assumptions that are inherently made, that the universe is flat. So usually when people talk about lambda CDM, it's like flat, silent, right? It's inherently assumed the universe is flat typically. Of course, you can let that be a free parameter, but the CMB data typically and other data sets tend to imply that the universe is flat, so people make this assumption. It is also assumed the universe is isotropic and homogeneous on very large scales, so on scales much larger than that of galaxies, and that the universe is currently dominated by dark matter, and then this thing, dark energy, which we're not entirely quite sure what it is. And then also there's a nearly scale invariant primordial power spectrum that's generated from something sort of like inflation, or maybe there could be some other mechanisms that generate this, but that detail doesn't precisely matter. So then, of course, these various principles and assumptions that we make in cosmology that are informed from observation form us to write down a specific metric. So this is the FLRW metric. I'm sure all of you are quite familiar, have seen this before, at least in some setting, taking a GR class or just in some cursory reading in cosmology. So you plug this metric into the Einstein field equations and you get two Friedmann equations that relate your metric variables, obviously, to the energy content of the universe. So typically these Friedmann equations, and so this is at the background level, the most D equation of cosmology, is it tells you how the universe expands as a function of what is inside of it. And so typically we rewrite these metric variables A, which is the scale factor, in terms of this parameter H, which is a Hubble parameter. I'm sure all of you have heard of the similar value called the Hubble constant. We'll get into a bit later when we talk about the specific model, a bit more about H naught. But I can quite simply rewrite that same Friedmann equation from the last page, wrong direction. This equation in a nice form where I have the Hubble parameter is just equal to the sum of all of these omega i's, where these omega i's are the fractional energy density of each constituent I. So I could have this cosmological constant, I can have radiation, I can have matter, I can have neutrinos, I can have all kinds of other things, and they all fit in this nice, simple way of writing the Friedmann equation. And so what are these 6 lambda CDM parameters? So there's 6 of them. It's quite remarkable, actually. You can get incredible agreement between theory and data for the most part, with the exception of tensions, and we'll get to that later. with only 6 parameters. It's honestly quite impressive if you think about it, right? Remarkable agreement with CMB, large-scale structure, the distribution of galaxies, 21 centimeter predictions, and it's only controlled by 6 parameters. So there's the baryon density today, the cold dark matter density today, and we work under the assumption that the universe is flat. So this is what's called the budget equation. So it basically just means the fractions all add up to 1. So 20% of the universe is this, another 80% is say this, and so it should always add up to 1 if the universe is flat. And one might ask, why is there no radiation in there? Because sometimes I get that question, but that's because we know the temperature of the CMB, so we know how much radiation there is. So that's something we can actually directly measure. There's an additional 2 parameters, which have to do with the initial conditions for perturbations generated from inflation. So this is the amplitude of the primordial power spectrum, and then also has a tilt, NS. We'll see a little bit more about that later. And then there's also H naught, or equivalently this other parameter theta S, the details don't matter. But this kind of, again, H naught is the parameter that's telling how much the universe is accelerating today. But typically people use this theta S parameter instead. These details aren't too important.
So flatness refers to what, spatial?
Exactly, spatial flatness, right? No curvature. And then the final parameter is this optical depth through ionization. This just comes from the fact that when stars start forming, they start reionizing the hydrogen that's in the universe, and so that makes it difficult for light to travel from the CMB to us today, so there's some attenuation due to that. And so you have this extra optical depth parameter you have to account for.
So just to count out the 6 parameters, are you?
Yeah, so there's 1, 2, so the baryon and the cold dark matter density, the amplitude of the primordial power spectrum and its tilt, H naught or theta S. People, yeah, it's an or. Yeah, some people use one or the other. There's a very simple relation between the 2 of them, but typically people use this theta S and then this optical depth to reionization. So you can see from this, this is very simple, right? There's not a lot of parameters that go in here, and you get all the richness of cosmology, with the exception of maybe there's some discrepancies in these cosmic dimensions. Again, we'll get to that later.
How can the approximation is it just 1 parameter for the optical depth reionization? It's kind of a complicated process that might take place over a period of time. Can you really calculate it with 1 parameter?
Yeah, it does work remarkably well, believe it or not. Yeah. Okay, so these are the parameters of theory. This is the model. How do we actually go out and measure those parameters? So I'm just going to use the CMB as an example because it's an easier one to talk about. So you have an experiment like Planck that measures.
Can I just ask you a question/comment? I guess on the previous page, some of this. Sorry,
You mean the budget
density,
equation?
this matter density stuff. Kind of these are parameters I can see go in the Lagrangian. They are the properties of what enters the equations. Those are more phenomenological.
Yeah, exactly. So this theta I, so this is a density ratio. So basically you've just rewritten this in a nice convenient way. And this is actually going to go to a little bit later, what I'm going to talk about later in the talk, is why you want to do this machine learning trick, because this is very much divorced from the theory, right? This is very much a toy kind of, as you say, a phenomenological type parameter.
On the right.
And you can imagine, so part of the problem with what I'll talk about when I get to early dark energy is people put a prior on this parameter here when it's something that's not well measured, right? And that can be problematic because you're totally ignoring fundamental theory. So you're absolutely right, this is completely phenomenological, but it works very well for, say, baryons and cold dark matter because it's very well measured, but I shouldn't say too much because I'm already going to talk about some of these idiosyncrasies in a bit.
And if I understand correctly, I is running from 1 to 3 here, is it?
Well, I can be, right, in principle, if you just want radiation, lambda matter, sure, it would be 3, but you can imagine anything else. You have neutrinos in there.
And the CDM has 6 parameters.
6 parameters.
Sum over I here includes what we know.
Yeah, so there would be the baryons, the dark matter, plus the radiation. Remember, we know what the radiation density today because of the CMB monopole, and then dark energy. Right? And so we find dark energy by using the budget equation, right? 1 minus everything else is 0.7. And of course, there's more detailed theories you can write down. There's also neutrinos and whatever, but that kind of is part of radiation too. So, but anyway, yeah, this is what's going on there. So importantly, so this is the model. How do we actually go out and how do we actually measure and determine what these parameters are? Because this is going to be very critical to the whole point of my talk today, right? So if we have an experiment like Planck, we create these great maps. So this is the temperature fluctuations on the sky. So if you look at the actual spectrum of the CMB, it's almost a perfect black body. So actually, if I throw up a true picture of the CMB, this would just be a totally uniform colored picture at 2.73 Kelvin. But these are actually the fluctuations that are 1 part in 10 to the minus 5, or sorry, 1 part in 10 to the 5 fluctuations that come from these initial seed, these primordial inflations or primordial perturbations for inflation. So these come from, this is exactly what this AS, I'm going the wrong arrow, this go the opposite direction, I think they're going. This is exactly what the AS and the NS parameterize. These are then evolved forward in time, and I can write down the power spectrum instead in terms of the spherical harmonics. So I have these CLs, which tell me how much power there are in each of these perturbations on the sky on a given scale. And you can see there's a characteristic peak here in the CMB temperature power spectrum. So again, we're just taking this image and we're putting it in spherical harmonics. We're calculating power for different Ls. And this is actually, this peak corresponds to that theta S I was talking about before. So people typically use this, but you can also rewrite, it's degenerate with H in a way. And from the theoretical side of things, so we want to compare to data with this likelihood down here. But in terms of theory,
What is the little small rectangular graph there?
oh, so this is a residual graph. So this is the full power spectrum with data points in red. Sorry, it seems a little fuzzy on the screen for some reason. But down here, it's just the difference between the model and the experimental measured values. So you can see that the error bars are basically overlapping with this 0 point, right? So it's a good fit.
So where is that peak now?
Where is the peak? Precisely what do you mean by the peak? You mean like what?
The highest point.
Are you asking like at what L it's at? So because it's about an L of 200, about the size of 1 degree on the sky. Is that what you're asking, or are you asking something different? In terms of like how much, I guess in terms of how much of a fluctuation above the background, this is that 1 part in 10 to the 5 fluctuation. So it's like a micro Kelvin, I guess, or so. So from a theoretical point of view, it's very easy for me to write down my model. And I can figure out roughly what the CLs, and with this equation, obviously you have to solve these Boltzmann equations numerically to actually get the full thing, but roughly speaking, this is what it would look like to get your CLs, is they depend on your power spectrum, which again, this has to do with this AS and NS parameter from Lambda CDM. And then there's also these delta Ls, which are transfer functions. And so basically you have to solve this giant set of Boltzmann equations, which is called the Boltzmann hierarchy. And these all depend on like Hubble parameter, omega B, omega C, so the dark matter baryons and all the other content. So this is where all the information Lambda CDM parameters are. And to determine whether or not my model is a good fit to data, I want to maximize the likelihood. So the likelihood for the CMB is actually a lot more complicated than what I'm writing here, but this is just like a simple basic likelihood. You're just trying to maximize the likelihood of the theory given the data that you've observed. And you have some covariance matrix, which isn't too important, but suffice it to say you're trying to maximize this likelihood function.
C is your covariance matrix.
Yeah, that's right. C here is, not to be confused with the CLs.
So what is the sensitivity of the apparatus that you can measure this 10 to the minus 5?
So you mean, I guess, you mean, I'm not precisely sure what you mean by the sensitivity.
Well, so you measure apparently 1 in 10 to the 5 difference in temperature.
Oh, you mean like how precise, how large are those fluctuations? Yeah, I guess probably like down to like 10 to minus 7 or so, or 1 in 10 to the 7. So another 2 orders of magnitude. So just roughly looking based off of this plot, right? So this is like 1 part in 10 to the 5 here, so that's like say 5,000, and then you're able to get decent measurements down to like 1,000, so, or sorry, down to say like a few hundred here.
So those fluctuations that you see at the beginning, they could be just due to apparatus.
Oh, you mean this fluctuation here?
Yeah.
So these fluctuations are actually due to cosmic variance. Because when you're decomposing the sky into, right, these spherical harmonics, for very high, for very large angles, but for low L, you only have 1 example, or 2 examples for L equals 2, then subsequently you only have 3 examples, so the statistical variance is very high on these low L values. But as you probe the power on smaller and smaller scales, you have a lot more modes, so your statistics go up as like square root n, right? So that's why the error bars get progressively smaller as you go left to right.
Oh, so the error bar is not constant?
No, yeah, it goes down as like roughly square root n. as you get more and more votes.
Sorry, what is that C inverse? I didn't understand.
Oh, so this is the covariance matrix.
So it's a matrix in what sort of matrix is it? What are the rows and columns?
So down the diagonal, it's just your regular like variance, right? And then the parameters off the diagonal are basically telling you the relative variance between two parameters in your model. So for lambda CDM, right, you'd have 6 parameters in this model.
Yeah.
And so down the diagonal, you'd have the variance from the data for each of those parameters, but then there's some correlation between each of the, any 2 chosen points together.
6 by 6 matrix.
Right. Yeah. But technically speaking, for the CMB, the covariance matrix is a hell of a lot more complicated than that because there's some other like nuisance parameters and stuff that need to be put in there that I am not an expert on by any stretch of the imagination.
It is just a 6 by 6 matrix.
In reality, it's not. There's other
Yeah, I would
nuisance
expect
parameters.
that there's an L dependence in it as well, but you've written it without an L dependence.
It doesn't need an L dependence. This is purely based on
Okay.
Okay, so this is, you want to maximize this likelihood function. So we do these experiments with Planck, WMAP, or whatever, or galaxies. We collect the data, and so then you can calculate these likelihoods. But then now you want to compare theory against that, right? But one of the difficulties in cosmology relative to, say, particle physics is that there's only one realization of the CMB, right? Now we have a couple different experiments, right? WMAP, COBE, Planck, that have all measured the CMB, but it's still the same CMB. So this is quite different in contrast to, say, people like colliders, like CERN, where they're able to repeat the same collision over and over and over and over again and collect a bunch of statistics. So they can look at the long-running averages and do a standard like frequentist type approach to looking at whatever they're interested in. Say, example, trying to extract the mass of the Higgs. But in cosmology, it's quite different. And it's really difficult. I mean, people do frequentist analysis in the context of cosmology, but it's quite difficult. So for this reason, in the last 2 decades, Bayesian Inference has become the gold standard of cosmology. And the distinguishing feature of Bayesian statistics versus frequentist is that you need a prior. And the backbone, of course, is Bayes' theorem. I'm sure we've all seen this at some point in our careers. And you have, of course, you have your posterior distribution, which is sort of telling you, you have some data and you go and fit it. What's the distribution of the expected parameters for that model? And then it depends on this thing called the likelihood, which is this function I was just showing before, sort of giving you an idea of how well your data fits to your model. And then there's this thing called the prior. And this is some extra information that you have to put in by hand, or maybe you don't know anything and you kind of have to put a guess in. But this is what sort of makes Bayesian statistics difficult, is because you have to actually say something about your prior beliefs on the distribution of the parameters in your model. And sort of what I'm going to be talking about today is if you're in a situation where your likelihood isn't particularly strong, the data sensitivity isn't so strong, and you choose a prior that's not so great, you can get very wrong results. And this machine learning trick we'll be talking about later, we'll get into that, but I shouldn't say too much more.
I don't understand this formula because on the left-hand side you have the same thing as on the right-hand side, but there's 2 other factors. Notation problem.
No, there's nothing the same on it.
Can you just say what remind us what is theta dm and exactly what?
Oh yeah, I should say what each of these are right now. So theta here are my model parameters, right? So on the left-hand side is our posterior probability. So it's the probability that I get these the particular distribution for the parameters on my model. So this could be my omega baryon, my amplitude and tilt of the primordial power spectrum, given the data and assuming some model, right? And then there's, of course, my likelihood, which is...
M stands for the model.
Yeah, that's right. So this is... Typically people drop this M, but I like to include it because you have to assume a model, and sometimes people consider other models. They might do Bayesian model comparison, for example. So there could be an M and an M prime or whatever. Not together in the same equation, of course. So then there's also this likelihood. The likelihood, again, is the probability of the data, assuming this is the correct model, given these model parameters. And then there's this prior, which is your prior guess for what the distribution of those parameters should be. And then this is your evidence, which is also called the marginalized likelihood because you've just integrated your likelihood over all possible data values. And trust me, we'll be getting a little bit more into the details of this actually very soon. So I think most questions should be answered. And part of what I want to do is sort of take that equation and conceptualize it a bit to help people understand. So there's a lot of very technical things that we could get into, but I don't want to do that given the time constraints. and also just given, the nature, very diverse audience. So we can still sort of think about this equation Bayes' theorem kind of conceptually. So what I want to do is I want to consider two situations, one where I have a very, very strong detection, and one where I sort of have a weak detection. And I'll make more precise what that means here in a bit. So let's first consider a mock experiment where we want to measure this parameter chi. This could be any experiment you want. It could be at CERN, wherever it can be in cosmology, it doesn't matter. This is just a toy example I want to do. So we want to measure this parameter chi, and the first case we're going to consider is where it's a strong detection. And what do I mean by strong detection is it means that I plotted here a mock likelihood. So again, this is coming from an experiment. You're able to write down the likelihood as a function of the model parameters. And a strong detection means that you have a very sharply peaked likelihood. So you can see quite clearly in this particular case at about 0.5 for chi, there's this very, very strong sharp. So this means your data has very strong sensitivity to the model. And then one could ask the question, okay, remember we talked about the prior, you sort of have to come up with this sometimes in an ad hoc way. Sometimes you may have previous information. But of course, sometimes when people add a new model or they're testing out something for the first time, they don't know what to put down for a prior. So it's pretty common to just put down a uniform prior. This is sometimes called an uninformative prior, but we'll see later why that's not actually a good name. But if you assume a uniform prior, given Bayes' theorem, right? If this is a uniform prior, that's just one, you can forget about it. So it's the exact same shape as the likelihood. So this is your posterior probability scales, just like the likelihood if you take a uniform prior.
What is P of D in this case?
P of
The denominator.
P of D. Oh, I should say this is the evidence, and for all practical purposes, with what we're doing Bayesian inference. You can forget about the evidence. It's just a normalization factor. So it basically just makes sure that it's a proper probability distribution. So for all practical purposes, you can just ignore it. But yeah, good question. I should have said that. But now what happens if we use an informative prior? Remember I said uniform is actually still informative, but let's imagine we use a slightly different prior. How does it change our result if we have a strong likelihood, a strong peak in the likelihood? Well, you can see here's this dark red line, which is my new choice of prior. And then the black is, of course, still the likelihood. And then this dashed line is the posterior, right? And you can see the posterior isn't too far from the likelihood. And remember, the uniform priors is right on top of the likelihood. So our results, even with this dramatically different prior, are consistent, right? They're within the error bars, right? They're within 1 sigma. Now you can imagine taking an even more incorrect prior, right? Assuming, of course, that the true parameter value for chi is at 0.5. And despite this, because this peak is so strong, even though my prior is so bad, right, the peak is so deep that it really can't sway the outcome too much, right? And so this is sort of just comparing them all together, and you can see that despite all of these different priors, the posteriors are fairly consistent with each other. And you can actually...
Sorry, you need the prior not to be too small around the peak. Otherwise,
yeah, if you're way down here, of course, you're going to kill off the peak entirely. But if let's say you're in the ballpark, but you're still not quite right. Right, I would say here, this is in the ballpark, but it's still really not quite right. But we'll see where it really affects it. So this is a fairly strong peak, right? So you'd have to really push this to really start to emphasize these little peaks that are kind of sub-dominant here, right? You'd probably have to start curving up over here somewhere or something. So we really have to be way off. But the point is that, generally speaking, a strong detection is fairly robust to these choice of priors. And then to go one step further to really drive that home is that the way it really works when you're doing these priors, and say we're doing something like measuring parameters in a lambda CM cosmology, is the first time we do an experiment, we sort of do have to guess. We don't know anything previously about the parameters. So let's just consider the example of WMAP, which is a predecessor to Planck. Again, this is not the real likelihood, this is just a toy.
Basically, what would the prior mean? It means that if I didn't do the experiment, this is what I expect to get. Is that what you mean?
It's sort of like you have some initial guess. So like, part of the point that we'll see later is that sometimes you can actually get a guess from theory, and that'll be the whole point of what I'm going to do later. Yeah. But sometimes maybe you just don't have any sense of it, right? You're using a phenomenological model like Sanjay was discussing before.
I'm going to make a random guess.
And you make a
guess is what the prior is.
Yeah, and frequently those guesses are when you have no idea. Typically they use these uniform priors.
Yeah.
Because I have no idea, so I'm just going to give equal probabilities to everything. Usually you'd only use this shape of prior if you already have some previous knowledge. But sort of to drive home the point that even if you have a bad prior and you do the same type of experiment multiple times, right? So let's imagine the situation we were talking about before, where we have this shape of prior, even with a strong detection. We see this is now our posterior, and imagine this was like a early W map. Again, this isn't the exact likelihood for I've just invented this likelihood. But imagine you did this experiment, and now this is the posterior you got, right? And then now say a decade later, when the first Planck data releases, I'm now going to use this posterior, or some approximation of this posterior, as my new prior for the new experiment that's measuring the same model parameters for the same data. Or even for a different type of data, even if I was looking at, say, the distribution of large-scale structure. Right, I now have some prior for that, and I'll use it. And actually, when I do a standard analysis for Planck, and I want to do lambda CDM, I use the priors from Planck 2018 on these different model parameters, even if you're doing a different extension of lambda CDM cosmology, because there is already some sense of what these parameter values should be. And what you'll find is if you iteratively do this, no matter what choice of prior you choose, unless it's wildly crazy, is always going to converge to the same posterior eventually, if you've repeated the experiment a sufficient amount of times. But again, this is critically important that this works for a strong detection, so for a sharply deep likelihood. Now let's consider a situation where now the likelihood is not nearly as well defined. And this is going to really be the crux of what I'm talking about today, because this is important in the context of cosmic tensions and if you're considering extensions to models, because issues like this can fairly readily come up. So let's consider a new mock likelihood where there's no well-defined peak. And we're going to assume that the true value of chi is actually minus 0.6, right? So again, this is just a mock example, but these type of things do come up, but it's a little bit easy to understand qualitatively. So if we look at this likelihood, at minus 0.6, we see there is roughly a peak here, but there's actually another peak over here at, say, about 0.4. So this is kind of problematic because, well, if I go ahead, this is problematic because of this thing called the look elsewhere effect. And you can see automatically, I think I have in a couple slides this for the uniform prior, but you can see immediately that if I just assume a uniform prior on chi, I'm going to say, okay, it's most likely speaking probably at 0.4, but that's actually wrong, right? And part of what's going on here and why these types of things can happen for a weak detection is something called the look elsewhere effect. And this is just a manifestation of basically when you sample a very large parameter space for a very large data set, and you scan over a wide range of data and you'll have a lot of parameters, the chance that you get a statistical fluctuation that's significant enough to call something a detection increases. So here's just a really simple example of where I took a Gaussian distribution centered at 0 with a variance of 0.5. So you can see I'm just now drawing samples randomly from that distribution in Python, nothing too fancy. And I've just drawn where the 5 sigma contours are. And 5 sigma, because typically in particle physics, 5 sigma is considered sort of the detection significance. But as I increase the amount of samples that I take from, what was it, 100? I think it was 100, right? From 100 to 10 million samples, you see now all of a sudden, now that I've taken 10 million samples, right, there's several points that are actually above that 5 sigma. And if I just naively look at a data set, and I don't consider about the size and the range of parameters and how many samples that I've taken, I can actually think that this is a real signal when it's not. Now again, this is very much a toy example when you're doing detections at CERN or whatever, you know, it's a lot more involved in this, but this is just to give you a feel is that if your parameter space becomes very large, the likelihood you get just a random statistical fluctuation becomes very high. And so you need to be very careful in describing anything that looks like a sharp peak in a likelihood to actually being a detection. And I should also say this is known in the statistics literature as the problem of multiple comparisons. So this is something that's very well known. And I guess I sort of already said this, is that if you have a wide range of parameters, this is bound to happen. But in Bayesian inference, you're actually able to naturally account for this look elsewhere effect, but with a caveat. If your prior is basically, you know, in the right ballpark. So basically what the prior does to avoid this look elsewhere effect is that it basically emphasizes regions of parameter space that are supposed to be the most likely for these parameters to take that value. And it sort of downweights the outer regions of volume that are sort of less likely. And so in this sense, using a prior is sort of able to avoid this look elsewhere effect by assigning lower probabilities to these more extreme regions of parameter space. And so going back to the flat priors, if I take the uniform prior, right? Remember I said that sometimes people call uniform priors as being uninformative, but they're actually informative in the sense that if I assume a uniform prior on a likelihood that has a statistical fluctuation that artificially generates a peak, it looks like I've now made a detection, but in fact I haven't, right? But on the other hand, if I have informative priors, so again, we're using this mock parameter chi, let's imagine that for whatever reason I know chi is supposed to be a negative number. And now I'm thinking of, okay, I need to write down a prior that somehow encapsulates that. So a very simple one to do is just write down a Gaussian prior. Let's say I basically have an idea of what chi should be. So let's say we center it exactly at 0.6, and we give it a variance of 0.5. And if I use that prior, you see that it actually now totally ignores this spurious statistical peak that I've said in this mock example. Chi is physical to be positive, for example. And now I've totally isolated this peak, and I made the correct detection.
So you have 0, and your prior has 0 on the right-hand side.
Not quite 0. It's a Gaussian distribution all the way, but it's very, very low values. Right?
Sorry, but I thought you put in the assumption there was, you knew that it was.
I mean, you could artificially by hand if you wanted to, but in this particular example, I didn't do that. Just do it quickly. But of course, you could do that. You could absolutely say it's absolutely 0 above there. You could absolutely do that. And actually, in practice, you should do that. But for the purposes of this plot that I threw together quickly, I didn't do that.
Sure.
But yeah, you're exactly right. If you knew that, you would say it's 0. Exactly.
You could also let it be uniform on the negative side, if you know it's...
Yeah, you could do that as well, right?
Yes.
But yeah, so these are all things where if you have some intuition, this actually helps you out, right? And let's say you just chose another prior, a different choice of prior instead, just this decaying function. You see that in this case, the posterior is actually now again correctly choosing the right peak, because again, we made the assumption that the likelihood that this comes from is where chi is minus 0.5. And again, this is just a toy example. The actual data doesn't always look like this. This is a very nice, clean, neat way to look at it. But conceptually, it drives home the point that if you have a good informed prior, you can avoid making false detections and artificially favoring some models over another.
I mean, in particle physics, they usually emphasize the look elsewhere effect.
Mm-hmm.
And so, but you still have a reasonable...
So the approach in particle physics is going to be a little bit different because they're not doing Bayesian statistics. So you have to do these different types of corrections that take into the amount of like the size of your parameter space, and you have to do corrections based off of that. So it's a little bit of a different approach to adjusting. You absolutely could, but usually people don't.
Is there a particular reason why they don't?
I just think it's more naturally suited to work in a frequentist type setting. I mean, I certainly don't want to speak for them because I'm not don't work on that stuff. But my understanding is that mostly they do frequentist-based analysis.
Do you not want to know why you got such a poor
why the peak?
extra peak?
Why the peak is so? Yeah.
Why did you
So
get that extra peak?
that purely comes from just the statistical fluctuation. So
But this is a probability plot, isn't it? So that means that statistical fluctuation occurs much.
So this comes precisely because of the volume of your parameter space is very large. The likelihood that one region in parameter space is going to have such a large fluctuation just becomes high.
Even though something is ruled out from being positive.
Right, but you have to put that information in yourself via the prior, right? So you have to tell it via the prior that region is good. A priori at the level of the likelihood, it doesn't know that, right? I can put any number I want into my theory, right? I mean, sometimes maybe putting a negative number is a problem, but let's just say it's like the slope on a power spectrum, right? It doesn't matter for calculating in the code whether it goes like this or that, right? It doesn't matter. You can actually write it down. Now, you might have some knowledge about, it should have a red tilt or a blue tilt or something like that, and you can have some information and put in your prior about that. But it doesn't prevent you from actually calculating what the likelihood would be for these unphysical parameters.
Yes. So what is the vertical scale then on the picture?
So this vertical scale, I mean, it's technically slightly different for the likelihood and the posterior. That's why I didn't label it. But this is a probability distribution, so this is just the probability. So just
The probability distribution.
yeah.
But it's negative, so it's not a probability distribution.
Let's say observable.
Is it?
Sorry, I don't know what you mean by it being negative.
Well, does it not go to 0 there at the right-hand side?
Well, you're talking about on the y-axis how it sort of dips down. Is that what you mean?
Yeah.
Yeah, this is a totally fake thing generated by me. That's a qualitative example. So yeah, this exact function isn't a proper probability function just because I didn't want to spend 100 hours, making a nice mock one, right? Is that what you're asking?
Yeah, well, if it is a probability distribution, if it's meant to be a probability distribution, and you get a peak like that, that means that there's large probability. It's not a single event. It happens often.
Yeah, but so this particular example isn't meant to be that way. This is supposed to be a relatively small fluctuation. This isn't supposed to be a very sharp increase. So if you thought of, okay, let's specifically look at the likelihood and be concrete. Forget about the dash curves, right? That's the posterior. If we're just looking at the likelihood, and you think of this in terms of like delta chi squared, I'm only talking about like a delta chi squared between these two peaks of only a few, right? That's very likely to see that kind of a fluctuation, right? This is a very weak peak, and that's the point, is that if it's a weak detection, you can get things like this. It isn't like this other case I was considering earlier, where we had a very well-defined peak, right? A statistical fluctuation of this size would be so exceedingly unlikely that you would never see it. So this is only like the borderline, like very small peak case, right? I realize this sounds very obscure, but the thing is there's been a lot of literature done that have, this is what the likelihood looks like, and people have made some very strong, bold claims about it, precisely because they were making the wrong choice of priors. So this is a very small statistical fluctuation, even though it looks big. This is just me trying to make a nice qualitative picture. This isn't exactly what the data precisely looks like if you're looking at it. I don't know if that better answers your question.
So is this all because you're measuring a very, very small change in a almost constant value?
Yeah, this is a very small increase. But if you choose a very bad, if you choose a very bad prior though, which is what happens in a few of these particular Hubble tension related models, is this can then look like a detection, even though this is like a nothing burger in terms of the actual size.
But I think the essence is really that you can't redo the experiment, so you can't gather more frequencies.
Exactly.
So,
yeah. So your hands are tied because you have the one CMB, and this is the likelihood. And the only way you can help yourself out is by using this prior knowledge. And if you have a very bad prior, which we'll see it in a little bit, that that's the case for some models, is this then looks like a detection.
I mean, I think we would probably say in particle physics that if I got that and I knew it was contradicting my physics, I'd say, well, if it's true, then something physics is wrong, so I should have to take it very seriously.
Mm-hmm. Right. So the
we
reason
have to do the experiment again.
Yeah, and I think the reason why probably the intuition in particle physics is different is precisely because of the thing Sanjay noticed earlier, is that frequently model parameters in cosmology are typically represented in terms of these phenomenological parameters like these omegas, which are density ratios, and not the fundamental underlying physics. So it's very hard, unless somehow you can calculate what that distribution of those omegas should look like, whether or not that's physical or not. And that's the problem. And so that's the whole point of what I'll get to soon. I should probably go faster or I'll take too long. But these are all really good questions. I mean, these are very nitty-gritty things. But let's see. Okay, so that's sort of like the spark notes of where we're going. Is that you have these weak detections that you need to be careful with the priors. But now, as I said before, is a very concrete example that I want to consider, and this whole work spurred out of a particular model, really, and a really long-term back and forth arguments between two groups of people on exactly how you should analyze this particular model. And it has to do around tensions and lambda CDM, and I'm sure a lot of you are familiar with some of these tensions because they gather a lot of headlines. So there's these tensions in cosmology, so there's the H0 tension in particular, and there are disagreements between direct measurements in the late universe, so typically with Cepheid calibrated supernovae data. And if you assume a model and you fit to the CMB, so of course people typically use lambda CDM, and the predicted value of H0 from that inference disagrees with this direct, in quotations, because it's not quite direct, right? It's a little bit in the past. They disagree, and it's fairly significant. So we can look at, over time, what's happened between the late universe and the early universe probes. So orange are the late universe measurements, and then purple are these early universe measurements of H0. And again, the late universe ones, they're inferred using lambda CDM, so that's where the model dependence comes from. And you can see that, like, over the last, say, 2 decades, almost 3 decades now, this discrepancy has continued to grow. There will be a caveat in a second, of course. I'm sure some of you are familiar with the recent caveat. And these direct measurements here typically relied on using this distance ladder measurements, which use a series of parallax measurements to nearby Cepheid stars, which then have a regular period luminosity relationship that then allows you to look at these stars in other galaxies, and then you see supernovae in those same galaxies, and then you use those to then infer the distance to further and further galaxies, and you can measure H naught. And it turns out that if you actually compare these two, the CMB results from Planck, to these measurements from Adam Rees and collaborators for H naught, naively this disagrees at about 5 sigma. So this reaches the typical threshold for saying, okay, there's a problem here. And I'm going to say the caveat, it's not in the slide, but some of you may have seen recently, which has sort of been my sort of gut intuition over, say the last 5-6 years or so, is that there could indeed be an issue with these Schu's results. So Wendy Freeman does have some results with different calibration methods that suggest that actually there may not be an H naught tension. But this model, and what we'll consider later, will just assume that there is indeed still an H naught tension, because the machine learning tools will learn will be quite
And the edge of the red giants are somewhere in between.
Yeah, they're right about here. They're about, say, 69, 68, somewhere in there. So yeah, they're fairly consistent with Planck. See, it used to be the case about 3 or 4 years ago where the error bars were large enough on the TRGBs that they were consistent with both. Right. So, Wendy would go around and say, oh, it's consistent with Planck, but then Adam could always argue, well, it's also consistent with me, right? And that's really not the case anymore. Although maybe he'll come up with some new argument or something. But anyway, we're going to go forward assuming for now, we're going to look at some H naught models and assume that indeed this tension exists. And I will mention that there is also some other tensions that aren't nearly as significant, specifically in the matter power spectrum. So this is what's called an S8, or the large scale structure tension. And specifically, it's a disagreement, again, between Planck and galaxy surveys in the measured amplitude of the matter power spectrum. And so there's a slight disagreement. Planck prefers a little bit more clustering of galaxies than we actually tend to see with some experiments. Although, again, which is funny, is you have these recent DESI results that seem to suggest maybe there isn't a large-scale structure tension. So it should be said that these tensions, they used to be a little bit more well-defined, but as of this moment, I think people are very confused about what's going on. There could be, again, maybe people aren't correctly accounting for systematics, but for our purposes, that's not the focus of today's talk. And I should say the sigma 8 parameter is just telling you specifically what's the amplitude, how much power is there in galaxies on this particular scale of 8 megaparsecs, which is about the scale of galaxy clusters to give you a sense of that size. And this is just visualizing this tension. So in gray band, here's Planck. This is sigma 8, and this is omega matter. Well, this plot's probably easier to understand. So this is just compressing this S8 parameter, and you can compare Planck here in gray to these collection of large structure probes. Some of them are consistent with Planck, but you can see some of them like here and then down here actually aren't all that consistent with Planck. They're at about 2.5 to 3 sigma, depending on the data set combination you choose.
They mostly seem to be consistent among themselves, which is surprising.
They tend to be, yeah, with themselves, they tend to be fairly consistent. Although, again, DESI recently is actually much further up here. And actually, I have some separate Lyman alpha stuff, which is a little different for these galaxy surveys that I've done recently, where it's also consistent with Planck. So it's probably the case that there could be systematics, again, that aren't being accounted for, people underestimating the size of their error bars, overestimating. But again, that's for the experimentalists to hash out.
But these are all on this, at that S8 scale.
Yeah, that's right. Yeah, broadly speaking, galaxy surveys, with the exception of DESI being a little bit of an outlier, but that's a very recent result. Okay, so one might be wondering, so why have there been these tensions, or why I did change the wording here today to why might there be tensions instead of why is there tensions, because it seems like, again, it's starting to get a little bit blurry. We'll see where it goes. But it makes sense that you could start to begin to see tensions in the standard model of cosmology precisely because lambda CDM is a macroscopic model. I outlined it earlier. It's very, very simple, right? So it may be the case that in the future, or maybe even now, precision cosmology needs a correspondingly precise sort of a UV completion of standard lambda CDM, right? Maybe dark matter's axions. Maybe we need to think of dark energy as being some quintessence-like model. So it's not too crazy to think that you could start having issues. But again, I'm less sure these days whether or not there is or not. Lambda CDM seems to be on pretty good footing as far as I'm concerned for the most part. But back to the point of addressing the H-naught tension. So now we're going to sort of transition towards the specific model I want to use as an application to drive home this theory-informed prior idea. So there's two basic approaches to addressing the H-naught tension. So one is trying to do some late time stuff. And for various reasons, this doesn't actually work out too well. I don't want to spend too much time into it, given time constraints. But it turns out the easiest way to actually adjust H-naught is by doing early time modifications to cosmology, specifically just before the CMB is formed. So just before recombination. And this is the most common, and it tends to work out the best. And the rough back of the envelope statement, and I can go more precisely after the talk if anyone's interested, on exactly how you realize increasing H-naught while not screwing everything else up, is typically the statement is you need to increase the energy density of the universe just before recombination by about 10%. Because that corresponds roughly, again, you can do a back of the envelope calculation, that corresponds to roughly a 10% increase to H-naught if you do that. And critically, this new component, whatever it is, it needs to peak at about 10% just before the CMB, but it needs to redshift incredibly quickly. So as radiation or faster, strictly speaking, probably actually faster than radiation given the more recent data analysis, but it has to redshift away very quickly. Because if it doesn't, it's going to mess up the subsequent evolution of everything else that we know works fairly well, like the evolution of large-scale structure. So it has to show up and then disappear very quickly. So it seems like a bit of a tall order. Now, probably, until fairly recently, the leading proposal for actually addressing Hubble tension has been this model of early dark energy. And anyone who peruses the cosmology archive certainly has seen fair amounts of early dark energy papers. And the basic premise of this model of early dark energy is that it's a scalar field stuck up with its potential due to Hubble friction. It's governed by the Klein-Gordon equation. So you can sort of think of it as sort of like a smaller scale inflation in a way. And so initially it's going to have an equation of state -1. So if you just write down the equation of state for a scalar field, if it's stuck due to Hubble friction initially, it's going to have an equation of state of -1. It looks like dark energy, hence the name. When the mass when the Hubble parameter becomes order the mass of the field, it will start to fall down its potential, and then it's going to oscillate. So if this was just a regular m squared phi squared potential, it would go from looking like dark energy to looking like dark matter. All right, just be like a regular type of mass term. But remember, I just said that in these Hubble tension models, this needs to redshift faster than dark energy, faster than radiation, so that'll be no good. So it turns out that people have typically, for this early dark energy model, use this sort of crazy axion-like potential. So typically for axions, you get these cosine potentials from instantons, but actually to get this to work, you have to use this crazy potential where it's like 1 minus cos to the n. I could complain about this for a very long time, but I won't. I don't have the time to do so. But it suffices to say you have to take this strange potential where n is roughly 3, or chosen to be 3 because it redshifts away fast enough. So it's sort of a scalar field with something kind of like a 5 to the 6 sort of potential. And so here's just a graph showing the evolution of the fractional energy density of the early dark energy field. We can see here this dashed line shows where the CMB is. And we can see the energy density is about 10%, and it redshifts away fast enough where it really doesn't affect anything but H-naught at the background level. And so this part is very important. So there's two ways that you can formalize or parameterize early dark energy. So you can work directly, it's supposed to be an axion-like particle, so you can either work directly with the theory parameters, the axion mass, its decay constant, or its misalignment angle, or what is frequently done, and in fact, with the exception of one analysis until this paper that comes out next week, had only ever been done with this parameterization of these effective cosmology parameters, is you can equivalently write this model in terms of this peak energy density and the redshift of what it peaks, and then you also still have to sample this misalignment angle. And so this is what I call the effective parameterization of early dark energy, because you have these effective parameters. And so this is sort of problematic, because what people typically do is they assume uniform priors on FEDE, CC, and theta I, but you're ignoring the theory bit, but I'll get to that a little bit later. So let's just talk about what happens when you assume these priors. If you do your MCMC analysis, and you include the Schu's prior with early dark energy, you actually find that you're able to solve the Hubble tension, which seems like a really great result. But actually, it turns out that this is a red herring, because you shouldn't be including a Schu's prior in your result if you're going to compare it to H-naught outcomes. But people had done this originally, but it turns out that's no good for just strictly Bayesian purposes. But the reason why it looks so promising is because when you do this, despite the fact that you've added in this incredibly new species into the universe just before the CMB is formed, and the CMB is incredibly sensitive to new things showing up. The shift in the power spectrum for the temperature and polarization power spectrum. Yeah.
Can you just tell me again why it's a red herring?
What did I call a red herring again? Was it?
It doesn't resolve the overtraction.
Oh, right. Yes. So this has to do with the using this. So strictly speaking, if you want to test concordance, so that's the whole point. Early dark energy is meant to restore concordance, right? CMB should agree with large scale structure and everything. The reason why it's a red herring is because you can't use the measurement you want to compare to in your likelihood, right? So this result relies that the shoes prior is used as a likelihood in your analysis run. So in a sense, you sort of artificially pushed towards the thing you want to compare to. So you should remove any information from supernovae when you do your fit. And ideally, you would want that to then produce this higher H naught, right? And that's how you should do it. And if you do that, basically this shift in H naught goes away.
So nobody made that mistake.
And initially, that was absolutely done. And we had a follow-up paper where we said that was wrong. And actually, there's been a ton of argument about whether you should include that or not. But from a basic Bayesian statistics point of view, that makes no sense to do, right? If you're trying to get compare to H naught with this model, but you can't put that information in beforehand. You're just going to sway everything. Right, so that's the red herring. But despite when you do that, you get this incredible fit to the CMB and everything looks hunky-dory. But then there's another problem that even if you do assume that incorrect choice of prior on the shoes prior in your analysis, that red herring, there's a significant conflict with large-scale structure. So if beyond the CMB, if you now look at what happens to the clustering of galaxies, you'll find here in green is Atlantic CDM, the best fit to CMB, and then red is this early dark energy model fit to the CMB, but now I'm plotting matter power spectrum today. And you can see there's roughly a 10% increase in power on scales that are in this blue shaded region that are probed by large scale structure. And 10% is way, 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 way too big of an increase. This makes that large scale structure tension I said before that was like at a 3 sigma level to like 6 or 7 sigma. So this is very much excludes early dark energy. And so then, okay, there's this disagreement in the literature I mentioned before on these things called prior volume effects. I don't want to get into it other than to mention there has been this large disagreement. But the nice thing is this machine learning trick I want to talk to you about here shortly will actually tell you that this prior volume effect is itself also a bit of a red herring. I can talk more about this prior volume effect afterwards if anyone's interested. I've given entire talks on this prior volume effect before, so it's a very dense subject that would probably take up too much time if I got into it for now. But suffice it to say that when you include large-scale structure, the model is very much basically strongly excluded. And actually, if you use the most recent Planck likelihood, so Planck has recently come out with new likelihoods where they've refined some of their analyses of the data. Even now, Planck by itself excludes early dark energy. So the previous likelihoods actually, for some reason, the way that whatever they were doing before, the likelihood was just in a way that early dark energy actually looked quite well with these previous Planck likelihoods. But now with the most up-to-date ones, for a selection of them as well, not just one, they have 3 newer likelihoods. It's no longer well favored. But now I want to get back to this choice. So the reason why I wanted to use this early dark energy model as a test of using this machine learning tool, which again, I'll get to in a bit, I guess I'm going to be going past the hour, that's fine, is that this case has been studied in incredible detail. There's a ton of data, a ton of information available on it, and people have spent a lot of computational resources analyzing this problem. So this is a very good test case to test this tool.
Just for clarity, precisely, which is the test case again?
The test case is this early dark energy model that I'll outline specifically what that is just now. Right, perfect time. So the test case that we want to do is, remember I said that people typically are sampling over these effective cosmology parameters, and this is very common in cosmology where we take some prior, usually uniform on some density ratio, like these omegas. In the case of early dark energy, this is typically taking on like this FEDE, which is the same thing as an omega, they just use F, that's the convention people use. It's a fraction of the energy density of the CMB, and also the ZC parameter, which tells you at what redshift this peaks. And people typically take uniform priors on that. And the reason why they do that is because convergence, if you try to sample from the particle physics parameters, if you're doing an MCMC analysis, takes an incredible amount of time. I think I'm going to say this again later, but it takes approximately 34 years of CPU compute time to actually do a Planck likelihood analysis sampling the particle theory parameters. And it just has to do with the fact of how basically there's only a narrow band where you have non-zero FEDE if you look in terms of the particle physics parameters, in terms of the volume of the parameter space. So it takes a very long time for the chains. Maybe you all aren't familiar with MCMC analysis, but it takes a very long time for the analysis to all the statistics to come out in a consistent way. And that's why people tend to use this other representation. And now I want to point something else out as well, is one thing you can do in the case of early dark energy is you can actually calculate what's called a profile likelihood. So you can, this is very computationally intensive to do. This is work not done by me, but others. Where it can actually calculate what the likelihood is, the maximum likelihood is along for different model parameters in early dark energy. And what you find is that the point, right, that's most favored, the highest likelihood point, this is delta chi squared, so just invert it, and then that's the maximum likelihood, or the smallest chi squared, is about only a difference of about 4 delta chi squared from FED of 0. So there is a preference for FED in terms of the actual likelihood is maximized at a non-zero point, but, right, it's only a delta chi squared of a couple. And remember what I said before is that you need to be very careful in a situation where you have a peak in your likelihood, right? So this is an actual profile of the likelihood now, not some mock thing I came up with. This is very shallow. This is only a delta chi squared of 4, and if I've added 3 model parameters on top of lambda CDM, it makes a ton of sense. I've added more parameters, of course I'm going to have a better fit, right? I now have 3 more degrees of freedom. So this can be entirely just from a statistical fluctuation that I have this peak, and it can also just be from the fact that I just have these 3 extra parameters. Now, depending on the data set you're using, how steep this peak is depends. Sometimes it's closer to 8, so that's a little bit more than this delta chi about 3. But you have to be very careful because the peak is so shallow. It's not a very strong detection of this early dark energy component. And remember that this is all done when you do the Bayesian side of things. This is the profile of likelihood. You are assuming uniform priors, right? So if I flip this upside down, right, I'm going to say, okay, and from a Bayesian sense, imagine I did my analysis, it looks like it should be that I'm making a detection of early dark energy of about 8%, which is exactly what you need to solve the Hubble tension. But remember, those priors are assumed on these effective parameters. Okay, so now almost gone into 55 minutes now at this point, but now we're actually going to get into okay, how do you get around this? How do you actually say something smart where you don't make this false claim that you've detected early dark energy? And that's by actually going back to the priors and trying to actually say something about the priors, what they should be from theory. Specifically, we would be able to put much stronger constraints on early dark energy if we can include information from, say, string theory and expectations for axions, because remember, this is an axion-like potential. So you can go to string theory and you can state questions about, okay, what should the distribution of the axion mass be? What should the distribution of the decay constant be? And the misalignment angle. We have people study this, and we can include this information in a prior to then learn a new informed prior on these effective cosmology parameters. Okay, I'm probably running out of time to do a thorough review.
We're not strict on time.
Okay, so if it took me like another 20 minutes, would that be kosher?
Yeah, another half an hour is no problem.
Yeah, I know this is a lot of information, but I promise it'll be worth it. So to actually do this, this is quite tricky. So remember I said you can actually sample these theory parameters directly. This is totally possible. Remember I said it took 34 total years of CPU time, right? That is a ton of compute time. I calculated how much energy that takes. That took the same amount of energy that it took to get the plane for me from Boston to Dublin. That entire flight, for everybody, the entire plane, that fuel, it was approximately the same as all the energy that was needed to compute these chains for this particle physics representation. That is a ton of energy. I don't remember the exact, how many kilowatt hours or whatever, or how many joules, but it's an enormous amount of energy that has been expended to study this model, specifically just for this one particle physics sampling case. So it's really not feasible to study it beyond the one example that I had shown here. So this is a paper that we've done like 4 or 5 years ago. Here's the constraint on FED with the particle representation, and this is the effective representation. And you see the posterior is different because the prior is different, right? That's why the shape is different. But that took an entire jet's worth of fuel to generate that one curve that basically says early dark energy is dead. But so this machine learning technique that I'm going to show you after I do a brief review of machine learning actually makes it so I can do the calculation in an hour, which to me is, that's crazy, right? You can do this in an hour. It's really remarkable. So just generally speaking, what is machine learning? I think everyone has a cursory, vague idea of what machine learning is, but machine learning is a class of artificial intelligence algorithms that basically are able to improve on various tasks that it's presented with solving by being fed more and more data and sort of updating its performance over time. And so in a qualitative way, what's the difference between machine learning and a traditional algorithm? Typically the way in computer science you would typically go after a problem is you have some data, right? And then you write down an algorithm by hand. One example is exactly doing the statistical analysis we were just talking about, right? Say our algorithm would be, let's write down what the likelihood function is and what's the model for lambda-C in cosmology. We now fit it to some data from the CMB, and then we get our output. Okay, what's the posteriors for everything? What's the best fit parameters? Versus machine learning kind of flips that all on its head. And instead, you give it data, you give it your desired output, and it learns the algorithm. And then you're able to flip it on its head and sort of then do a traditional algorithm type approach. So it's a very different way of doing problems. And there's many, I mean, I've listed some here, but there's, hundreds of machine learning algorithms that people have invented. They're all better suited for different tasks. Some are very well suited to doing image problems. Some are very well suited to doing language problems. Of course, we're all familiar with like ChatGPT. And generally speaking, why is machine learning so useful? So it's very good at taking a problem that's very high dimensional and reducing it down to something that's very simple, easy to understand, or easy to actually play with, right? So imagine trying to write an algorithm by hand to classify between a cat and a dog, right? That's going to be pretty hard to do. But because of the complexity of the architectures in machine learning, they're actually able to learn this through a bunch of sophisticated techniques I don't have time to get into. But they're also very good for like generating new calculations or sampling new parameters or new examples from a distribution. You can train on some distribution of examples, say images of cats, and once it's converged, you can then generate on the fly new images of cats that haven't even existed yet, as an example. And of course, there's some downsides to ML, and I've been kind of critical myself of some of them. In particular, sometimes machine learning can be a bit of a black box. It's sometimes very hard to understand precisely what's going on. I mean, people will talk about you can open up a convolutional neural network that's been trained on animals. You can see like features in the architecture that look like ears or whiskers or whatever. But still, to me, I've never felt like, machine learning algorithms aren't always great about really telling you precisely what's going on. And as a physicist, that can be a bit frustrating, right? You want to understand what's going on in a problem. And machine learning has been applied to a lot of different contexts in cosmology. Myself, I've done it a lot in the context of gravitational lensing and dark matter substructure, trying to identify different types of dark matter. But people have done it for all kinds of different things, increasing the speed of simulations, detecting anomalies in data sets, large-scale structure mapping, CMB, of course. So there's a lot of wide-ranging applications. But one particular, I don't know, say about a year ago, I basically felt like I was done with machine learning. I was kind of, this black box thing to me seemed like something, a lot of people use them and they kind of use them for problems you could use without machine learning anyway. So I was kind of having a falling out with machine learning. But then when I got to MIT, I was talking to some people there about these normalizing flow type architectures, and it kind of won me over. And so this project sort of came out of it. And the gist of what a normalizing flow is it's sort of a machine learning architecture that's very good about learning very complex probability distributions. And the way that it does this is it learns a series of invertible transformations from a very simple distribution to a complex distribution of your interest. And specifically, it has to be invertible. I'll kind of blow through it a bit, but fundamentally what's going on is just a change of variables formula. So you're sort of doing this mapping between these two spaces. And typically what you do is you choose, there's a target space, which is the distribution you're trying to learn. So this particular example I'll talk about later is this early dark energy parameter space. And then you're trying to learn the mapping between that and a much simpler base distribution, which you typically choose to be something that's very simple In this case, it's usually a Gaussian. So you're able to sample from this nice, easy land of Gaussian distributions, and then using these machine learning algorithms, I'm able to learn this mapping into the distribution I'm actually interested in. And why do I want to do this? Is this allows me to very efficiently sample that parameter space. And so I need to learn this mapping between these two distributions, the one I'm interested in, and this very simple one that's very easy to do these calculations in. I need to learn this mapping. How do I do that? Well, what I have to do is, of course, I need to get some data. That's how machine learning works, is it relies on using data to train them. So I need to grab some samples from my distribution. So in the case of what I'll talk about early, or a little bit later, is in the case of early dark energy, I just have a bunch of examples of simulated cosmologies for early dark energy. So these are my theta with different parameter values, and those follow some distribution. And what I now want to do is I want to basically train these architectures to learn the transformation from the simple base distribution to the distribution of early dark energy parameters by tuning a neural network.
The way you've set it up, the dimension of the space of parameters should be the same.
Yeah, so the dimension of parameters here is 11. So there's the 6 lambda CDM parameters plus the 3 theory early dark energy parameters plus the 2 effective. You might wonder why there's not 12, because the misalignment angle is shared between the 2. So there's 11, the dimensionality of the space is 11. And so the way that I learned this distribution, so this is going to be some complex distribution between omega baryon, between H naught, between the axion decay constant, FEDE. In this 11-dimensional space, there's some complex distribution, how all these parameters rely on each other. And I can learn that distribution with this machine learning algorithm using standard machine learning techniques like stochastic gradient descent. Don't worry too much what that means. It's just an optimization process. And once I found the optimal point that maximizes the negative log likelihood, it turns out just the way that normalizing flows are constructed, that you actually have now learned a proper bijection between one point in your base space to your target space. So
how is such a function F represented?
In this particular case, it's represented as a neural network. So you can, of course, write down the people in a simpler form of a normalizing flow. You can actually write down a very simple analytic expression that's invertible. But in our particular case, you actually can use a neural network to represent F. So F is just some mapping between two spaces, right? So neural networks are very good about being a mapping between two different representations, right?
So it's discrete.
No, in this case, it's continuous.
I don't know how a computer can work with continuous variables.
I guess precisely what do you mean by what do you think is discrete versus continuous? Just to be clear, do you mean the values the architecture takes, or do you mean the parameter values?
I don't know. So they're real values that you put in. So like computer real values. That's what
yeah. So they're continuous values for all of these lambda CDM parameters, and then the architecture just learns the mapping between these. So there's no, this is all continuous. There's nothing. The only thing that's discrete is that there's 11 parameters. Yeah, sorry if it's not making a ton of sense. I am kind of skimming over some, details for the sake of time. I've already gone a little bit too over.
Sorry, so speaking of parameters, I guess the neural network, so as its layers and there's weight matrices and so on, you're not talking about that, you're just talking about the input and the output.
Yeah, that's right. Of course, those are details I could, give you information about if you wanted to, but conceptually, just thinking about what regular neural networks do is all you need to, just learning this mapping, right? Y equals mx plus b is like the most basic neural network architecture, right? Just make them matrices and vectors or whatever, right? So you're just learning this mapping between y and x, right? So now what we want to do is, okay, now we're finally getting back to where we started from, is the importance of having a good prior in the specific case where you have a likelihood that's very weakly peaked. So what we want to do in this particular case is we're going to use these normalizing flows to learn a new prior on these effective cosmology parameters by training on a distribution that is sampled from theory expectations for axions. In particular, if you just go to the string theory literature on axions, you'll find that it's expected that the axion mass and decay constant should be log distributed. Also that the decay constant shouldn't be above the Planck scale. They should all be decently well below the Planck scale. So we include all of that in our simulations. And also, I guess this is the same, but that's the field excursion. So in addition to the decay constant, it's also really not a good idea to have too many Planckian field excursions as well. So just by embedding all of this knowledge we have about axions into our simulations and then training on a normalizing flow, we're then able to learn the mapping between these particle physics priors onto these priors that are much easier to actually do sampling with.
So you just mentioned two words, string theory there. Did you use any string theory in choosing these physical physics parameters?
We did. I mean, we didn't. So people have studied.
That makes me upset because you say yes.
Okay.
Because is it really reliable to do that?
I mean, this is a choice you can make. So this could be a constraint on string axions, right? It doesn't. Maybe you have some other, opinion on what the distribution of, axion decay constant should be. So I mean, if you have an argument for that, then you can include that in a prior. This is just a choice that we made. But one of the other reasons why is if you want to form this cos-q potential, you really can't have values for the decay constant that are actually very close to the Planck scale anyway. Just even throwing out string theory arguments, just the structure of that potential, you get these higher order operators that show up and would ruin it.
Do something instead.
Sorry?
You'd be stuck if you didn't do something instead.
Yeah, you'd have to probably do something quite similar anyway, right? But we particularly went to the string literature because people have actually studied these distributions in great detail. So it's a very concrete thing we could say. The whole point of this is to display the technique, less so the precise result. So we just made this choice, and of course you could have a different prior, and you get a different
The
result.
logical structure is that you need that to us.
Yeah, that's right. And the point is, the difference here is we're now actually doing this for the first time. Because when people sample over these parameters themselves directly, that's completely, you're throwing any physical knowledge out the window, right? You're just going off of like energy density ratios, right? That's really, you can't say anything about whether what's going on is physical in the underlying model. So yeah, precisely what we're going to do, I guess I just said this, is now what we're going to do is we've trained these normalizing flows to learn the mapping between the theory parameterization and the effective cosmology parameters. And that then allows us to actually go out and update constraints on this early dark energy model in a very efficient way. The only thing you have to do first is, of course, you have to train your model. So to do so, we do 10,000 simulations of this early dark energy model. Sampling again in this theory representation with the uniform priors on log m and f. We restrict the Planck scale, the decay constant to be below the Planck scale, and we train this architecture until it reaches convergence. So this is this negative block likelihood I had mentioned before a few slides back, and we can see that what I'm plotting here is both the training and validation loss, and just the poor man's understanding of what's going on here is that you can see both the red and the black curve agree with each other. The architecture has never seen the red data. So both losses are asymptoting together, so it's reached convergence. And this only takes 10 minutes to train. It took me, say, 20 minutes to make these 10,000 simulations. That's pretty cheap. And it took me 10 minutes to do this training on a GPU.
So just to understand, you have a training set, and you have another set of samples.
That's right, yeah.
You're just saying.
Yeah, I don't say here, but I have the 10,000 training samples that create the black curve.
Yes.
And then I have an additional 1,000 simulations that I withhold. The architecture never sees, the weights are never updated based on them, that I then use to verify that I'm not strictly memorizing what I gave it. And that's what's called overfitting, and you have to be very careful about that. And that's precisely why people will make these plots, to show that samples it's never seen are correctly accounted for. And so once you've trained your normalizing flow, what you can then do is you can then sample from that distribution, from that normalizing flow.
Can we just go back?
Yeah.
In both your red and your black, there are these, the peaks seem to be correlated. Yet, so why is that?
Yeah, I mean, that's not too surprising. So that it could be just the case that, what's happening is you're moving around this lost landscape and you're adjusting all the weights in the architecture. And since there's so many points, right, I mean, there's 10,000 examples for black and 1,000 for red, that's a pretty decent representation of the distribution, even with just 1,000 samples. That you're sort of, I think the reason why they track so closely with each other is because they both kind of represent the distribution well to begin with, right? So you would expect, as long as it's not overfitting, that they should be roughly correlated, right? If it's performing well, you would expect there to be correlation, I guess is what I'm saying, right? If it's properly learning the underlying distribution with the training samples, I would expect the validation to sort of follow as well, right? And so what we can now do is we can sample from these normalizing flows that we've constructed. And so there's two different choices of priors we've actually made. Is the strict particle physics, or axion, string axion type prediction, where both the mass and the decay constant are log distributed. And then we have a second choice of prior that we use because that one analysis I mentioned before that people had done where they had sampled, well, I guess where we had sampled. It took 34 years of computation time, we actually used this choice of prior. So that's why we have two normalizing flows we've trained. And importantly, what you can see here, this is our learned prior for early dark energy for FED and also ZC. Now remember that all three of these were supposed to be uniform priors. ZC, okay, fine, that's not quite uniform, but it's kind of uniform in some areas, right? Here, the axiom is aligned at an angle, yeah, okay, that's fairly uniform, but here, right? That is anything but uniform, right? So that goes to tell you that when people have done all of these previous analyses, and no knock on them, there's a reason why they did it. It's again, it's too computationally expensive to do anything else. Is that prior was completely wrong, right? And remember that we had a peak in the likelihood. It's probably hard to tell, but this curve comes all the way up here, right? So this is very strongly favoring small values for FED. There's a peak of about, it's 8%, 9% is where the peak in the likelihood is when we showed you the likelihood profile. So when people are saying they're detecting early dark energy, that really can't be right because, right, this is the correct prior to have for that particular choice of model. And on the right-hand side, what I'm doing is I'm just comparing some naive binning. So someone might ask the question, why didn't you just do a bunch of simulations and just bin it and then sort of fit a curve to FEDE, ZC, and theta I, sort of get a cheap prior? Well, the reason why you can't do that is because these parameters all depend on the other, right? FED, ZC depend on the other 9 parameters, right? So this particular approach actually doesn't correctly account for it, and you can see how dramatically different the shape of these distributions are. So you would actually have made an incorrect assumption. And how do I know that this choice is correct? Well, the reason why I know it's correct is because I had said before, we've actually once before sampled this distribution, and it's a little fuzzy to see here, but red and green effectively correspond to green is directly sampling the theory parameters. That's the curve that took an entire jet's worth of fuel energy to create this green curve. And then red is our normalizing flow generated posterior in red. So what you want to look for here is see that both the red and the green are basically consistent with each other on all of these plots. So FED and ZC, they're within some statistical variance. They're not quite on top of each other, but they're very close to each other. And you can see the same thing here for log 10 ZC, and then also theta I. Now you might wonder what's going on with this bump. That has to do with the choice of priors that was made. So that has nothing to do with the normalizing flow. That has to do with how many samples were collected in that region of parameter space. I could talk more about it later, but that doesn't have to do with the normalizing flow, this peak down. But the takeaway should be, that took me an hour to make the red posterior. The other one took a month on 400 cores at a supercomputer, which is very, very efficient in terms of generating these constraints. And this is just for a CMB likelihood. And so the new thing that we were able to do is, now that we had this in hand, we could for the very first time put the strongest constraint on early dark energy that for all practical purposes completely rules it out. At least that's what I would say. Some people might say maybe this threshold was good enough. But what we did is we can use the likelihood of Planck plus some large-scale structure data. Remember, large-scale structure data starts to strongly disfavor this model. And these likelihoods are very, very complicated. To actually think of trying to sample this with this particle physics representation, just Planck and CMB took a month. This could have taken 3 months, 4 months. I don't know how long. I don't think anyone would have wanted to have tried doing this sampling. But with this normalizing flow, we're able to generate it once we've had it trained. 10 seconds, you have this posterior here. And we find that we're able to increase the constraint from the fraction of energy density in early dark energy recombination from being at about, say, 5.5%, 6% at 95% confidence, down to about 2.5%. And the real kicker is that the H0 value is now about 6 sigma away from shoes in the early dark energy model. Right, this model is supposed to address the Hubble tension, and clearly when you use the particle physics priors, this is now precluded. It cannot restore concordance. And this is very convincing. Before it was closer to like 4 sigma. So now this is 6 sigma away. That's pretty hard to argue with. And then I should say, I sort of reiterated this or sort of hinted at this already, is this approach is very easy to do. Once you've had it trained, this is all the lines of code you need to generate that posterior, right? 1, 2, 3, 4, 5. Once you've trained this model. So model, you store the model in some file, and then you're able to load it, update your priors in post-processing, and you can generate these constraints on the fly for any likelihood you want. And then I guess save a bunch of trees in the meantime. Okay, so I guess I've gone on maybe a little too long, but anyway, to conclude, hopefully the point of this talk again was to sort of show by example, but what I've sort of demonstrated here can really be applied much more broadly, right? With the point being that these normalizing flow architectures can be used as a very concrete way of mapping between some information you may have on some model or some parameter you have of interest, where it might not be very easy to map between a theorist's representation of what's their model to actually how an observer might go and constrain that model. So in particular, the case of this axion decay constant, what was tricky in putting the theory priors was that the MCMC analysis was very cost prohibitive. Right, but by using this machine learning tool, we were able to basically, by a factor of 34 years of compute time, speed everything up. And really, this could be applied to anything. This doesn't have to be cosmology. This could be particle physics, any place where there's a Bayesian type analysis where you need to learn some distribution. Because remember, machine learning is very good at taking very high dimensional complex problems and boiling them down to something very simple. So the application of this more broadly is very wide. There you go, find the words. Yeah, I hope you found this interesting. Maybe I was kind of covering a lot of very technical topics and trying to review a lot all at once. But I think the end result could be very critical, especially when you're considering very large models with tons of parameters, where you could be susceptible to these things like look elsewhere effects. And then, save your face, I guess, by not making an incorrect assertion or assertion. That'll be all.
Thank you. Any questions?
So it's the early dark energy that you're hitting on the head with this phrase, this second last sentence. So what is the next stage in this Hubble game that you could expect?
Oh, so yeah, there are ways to get around this. So I actually have a model myself. And it's also an axion-like model, but if you actually consider an axion with this moduli field as well, so okay, call it a dilettante, but it's not really a dilettante. But you have some mixing, so you have two scalar fields. One is an axion, one's a dilettante, but if they're coupled in the level of the kinetic term for the axion, in this two model case, you can actually get something that looks like early dark energy. It has the correct energy injection, 10%, and then it redshifts away fast enough without having a contrived potential. And the other thing is that that extra moduli field then acts as a form of fuzzy dark matter that then actually suppresses large-scale structure. So it solves H0, and it suppresses large-scale structure to be consistent with both S8 and H0.
At the price of introducing this dilettante?
Right, exactly. And precisely what kills early dark energy is large-scale structure. So this two-field model, which has actually this, you can write it with the same amount of parameters as early dark energy. So it's not even an extra number of parameters. It has all the features you need to actually keep the large-scale structure problem away. We're working on the data analysis for that now. It's quite tricky to do with the two fields, but initial looks, it seems to be promising. But anything basically the point would be anything that just does energy injection like this is not going to work. precisely because you need to add more dark matter in the universe. If you only do that, because you run into this issue with the integrated Sachs-Wolf effect, which is like a very detailed CMD thing. But the only way you can solve that is by adding more dark matter. So to get around that, you have to do something else somewhere to compensate for this. So there are models that have been proposed to do this. I personally don't think there is an H-naught tension anymore. It's only shoes is such an outlier. There's been so many models proposed, and shoes always seems like, there's something off with it, just in terms of just looking at how the data behaves and how the data seems consistent with each other. And I think really, the Wendy Friedman results are sort of adding some ammunition to that argument that there probably aren't these tensions, but I think there's a lot of lessons that can be learned from, the 10 years people are thinking about this, and this hopefully is one thing that can come out of this is, how do we think a little bit more intelligently about how we actually constrain these extensions to lambda CDM, or just any extension to any, established model, especially when we're on sort of a threshold detection, right? The early dark energy was never very strongly detected. It was always like a borderline, okay, this is kind of just barely maybe being detected. Yeah.
Okay, we'll have plenty of questions, but we can continue. Mike's around for another couple of days, or tomorrow.
Yeah, tomorrow.
So let's just thank you again.
So do I understand correctly that your method is ideal for constructing prior?
Yeah, exactly, right. And we actually use this method in some other contexts as well, but not on like model parameters. So there's another thing that I work a bit on is something called the effective field theory of large-scale structure. And one of the things that you have to, that's been a problem in that particular approach to modeling, galaxies, is you have to have all of these things called bias parameters, in your expansion. And these are nuisance parameters. And there's been a lot of argument over the choice of priors that you need to make on these. And we use, the first thing we actually did before this is we use these normalizing flows to train on very large n-body simulations of galaxies to learn a prior for these bias parameters. And when you do that, you actually increase the constraints on things like S8 and sigma 8 and H0 by like a factor of 2 or 3. So really, something like this can be very fruitful for not even necessarily just looking at BSM stuff, which typically I'm more interested in, but even just like more vanilla cosmology or Bayesian inference applications where maybe, in the particular case I just mentioned, right, you have these very large n-body simulation boxes that take, months to generate, right? And there's these very, tens of gigabytes of data. And this normalizing flow is able to then extract information about these bias parameters from this very complex, data distribution, and then distill that and increase constraints by like a factor of 2.
Yeah, and if I understood correctly, you should choose your target distribution at the end. And how did you do that? The one that you're mapping between two distributions, the one that...
Right, there's a mapping between this base distribution and the target distribution, yes. Right? So the target one's the one that you're interested in itself, right? Yes. So in this particular case, it was like...
You choose the base distribution.
The base distribution, yeah, you chose that to be simple. So in this case, people usually just use a Gaussian.
Okay.
Because it's very simple. So the point is you want to have a Jacobian in particular that's very easy to write down.
You're typically going to choose to be a Gaussian.
Exactly, yeah. Almost exclusively.
Find the transformations that get this to a Gaussian.
Exactly. Yeah. So I think it's a very nice tool. So we'll see if anyone else can come up with other applications of it.
But that can be quite restrictive as well.
And I guess I didn't say, I think the nice thing about this is, remember I complained about black boxes and I was kind of having a falling out with machine learning? It's very clear what's going on with normalizing flows, right? It's not so mysterious what's going on, right? It's not like, how did this thing figure out how to like generate images of cats or classify between a cat and dog?
Very well. It's,
right?
It's clear, but it seems to me that that unless I guess a reasonable normalizing, a reasonable target.
Or do you mean the base?
The base distribution. Unless I choose it to be reasonable, so that the mapping to it is supposed to be 0 essentially.
So actually, I don't think it says big of a deal as you think, because where all the hard work is actually done by the machine learning architecture itself.
But supposing it's actually 2 Gaussians. That is what really
you mean go
here.
So
mapping 2 Gaussians into 1 will just be wrong.
You could do this with a normalizing flow. Yeah, we've mapped bimodal distributions. I mean, in a way, there is a semi-bimodal distribution in early dark energy. I can find it. I don't know. Maybe I'm not thinking of it precisely what you're suggesting. Let's see. I mean, this right here, right? See this black curve?
Yes.
So this curve you can see is somewhat bimodal. It's not fully bimodal.
It's somewhat bimodal.
And we can handle that no problem. So because what we're doing is we're learning the mapping on
But
this plot.
if there was a reasonable region of absolute zero between those two peaks.
See, I don't see why I don't think there would be an issue with that. I don't see why. I think the machine learning, if you choose a complex enough architecture, I don't think there's any distribution that would really throw you off. I mean, this is just the nature of machine learning algorithms, is they're very, very flexible.
I mean, I'm thinking that the topology of the space, the two spaces should be the same.
You mean between the two modes?
Yeah, I'm trying to capture something here, this distribution. If it's a change of variables from one space to another, then the topology of the two spaces at least should be the same.
Oh, okay, maybe I understand. Okay.
Maybe I can't change variables from one space to a space that's completely different to it topologically.
Yeah, I guess I
I'm
can.
trying to give you one example. Pi not being zero, being down zero, whether you have two separate spaces and you want to map one space to the two of them. Change of variables doesn't look like it would be the right thing to do there.
But it almost sounds like you're treating the two modes of the distribution as like separate things, though.
They are in some sense, because changing variables change a variable. I'm thinking just geometrically. Space, which I can do with all its diffeomorphisms, I can do any of those ones, but if two places are not diffeomorphic.
Okay, I see. Yeah, I don't know. That's a good question.
So,
Thank you, Mike. Is this normal?